hopefully this is working. We'll give it a try. And I left off, I was about to talk about the atom. So everything, all matter, for our purposes, all matter is made of atoms. Atoms have a nucleus. Don't get confused between the nucleus of an atom and the nucleus of a cell. A cell is composed of millions and millions of atoms arranged in various thousands of molecules. So an atom is extremely small. You cannot see an atom with a microscope. You can't see an atom with an electron microscope. Very, very, very tiny. We won't go into how we know what we do know about atoms, but let's just point out that there is a nucleus, a center point with protons and neutrons. Protons are positively charged, neutrons are neutral, and electrons that are spinning around like this are negatively charged. And for any element, the number of protons equals the number of electrons. If you change the number of electrons, which you can do, an atom can take on an extra electron or 2 extra electrons, or it can give up an electron or give up 2 electrons. So that change in the number of electrons affects the charge of the atom. So if number of electrons equals number of protons, the atom is neutral. If there are more electrons than there are protons, then it's negatively charged. It has more negative charges than it does positive charges. So this is a negatively charged ion. If an atom has this many protons and takes away some electrons, then it's positively charged. The positively charged protons have more positive charges than negatively charged electrons. So you can change the number of electrons, and that's going to change the properties of how that atom behaves, but it doesn't change what it is. So it's sodium, whether it has same number of neutrons or same number of electrons as it does protons, but typically sodium loses an electron, and so it's a positively charged ion. You cannot change the number of protons.
Oh, by the way, my
If you change the number of protons, then it's a different element altogether. So that can happen. It happens in stars all the time. Stars are making new elements, but you no longer call it the same thing if you change the number of protons. The model that we have for the atom is always drawn incorrectly, and I'll explain why in a moment. But here we see the nucleus with positively charged protons, neutral charged neutrons, and negatively charged electrons. In terms of mass, protons and neutrons, they weigh about the same, so we'll just call it 1 atomic unit for each one. Electrons are much, much, much smaller mass. So they have a full charge, a full negative charge, equal to the positive charge of a proton, but mass, they hardly contribute any mass at all to the atom. Okay. We arrange atoms for our own convenience. Elements, we arrange, an element is just pure matter of only one kind, and we arrange them in what's called the periodic table of the elements, and there are lots of numbers and things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The numbers equals the number in the upper left corner there, that equals the number of protons. So hydrogen has 1 proton, and it has 1 electron. Helium has 2 protons and 2 electrons. Lithium has 3 protons and 3 electrons, and so on and so forth. Carbon has 6 of each. Oxygen has 8 of each. But again, you can change the number of electrons. You can change the number of electrons. The columns of the periodic table, elements in the same column have similar properties. So this first column, they are similar in their chemical properties because they would all like to give up 1 electron and become positively charged ions. In the next column, these guys can give up 2 electrons and become a positively charged ion with 2 positive charges, calcium plus plus or magnesium plus plus. Over here, this end column, These are the noble gases. They have their outer shell is full. Electrons arrange themselves in layers, kind of little electron clouds, and let's just not get into too much detail, but these guys, their outer shell is full. And the reason you would add or take away an electron, like why would these guys give up an electron? Because then, right now, they have one electron in their outer shell, just one. If they give up one electron, then their outer shell is full. So in other words, they had a full outer shell, but then there's one extra electron that doesn't fit in this shell. So that extra electron is buzzing around. And if they could just get rid of that, then they'd have a nice, full, stable outer shell. So they'll just give up that electron to keep the full outer shell. These guys have a full outer shell, so they're not interested in other chemicals at all. They don't want to share electrons. They don't want to give electrons. They don't want to take electrons. They're the noble gases because they're like, I don't need you. You're not good enough for me. So they're just completely non-reactive. Helium, neon, argon, krypton. They don't even interact with themselves. Two helium atoms don't want anything to do with each other. Two neon atoms couldn't care less about each other. Now, an interesting thing with neon, argon, krypton, and xenon, these are gases. We'll put them in tubes like neon lights. We'll put the gas in a tube and we'll force electrons onto them with electric charge. And as soon as the atom, you force an electron onto it, it is so anxious to get rid of it. It's just like, I don't want that. And it just throws it off. And it throws it off in a way that it creates light. So this is how we have neon lights. It's just neon gas in a tube, and we run a little electricity in there, which it's forcing electrons onto the atoms, and it just gives it away immediately, and then it throws that one off, it throws that one off, and we just keep adding them, and they keep throwing them off, and that's how we get lights. And you can do that with argon, krypton, xenon. This column next to it, these guys are almost like noble gases, but they need one more electron to have a full outer shell. And so they will readily take an electron. Chlorine is very reactive. It wants an electron. So here's sodium, wants to give up an electron. Here's chlorine, wants to take an electron. So these guys form natural pairs. So here's sodium, and it really wants to give an electron. Here's chlorine, it really wants to take an electron because it has its outer shell holds 8, and it's got 7. And it's like, please, 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 just give me one more electron. That's all I need, one more. Beep. And then it's happy. And it's negatively charged, but it's happy. So sodium and chlorine get together all the time. If you have pure sodium, it's very reactive. And it will explode when in contact with air or water. So pure sodium is extremely reactive. Pure chlorine, very reactive, very dangerous. You put the two together, they react, and it becomes sodium chloride, which is just table salt, and it's completely non-reactive. So the chemical properties have changed because now they're happy, they're content. Sodium gave up its electron, chlorine took its electron, no more reactivity. We're not going to go too much into this, but these guys in the second column, in this column here, 2 away from being noble, they would like 2 electrons. Oxygen tends to, it doesn't necessarily take them, it's willing to share, but it shares kind of unequally. It's like, let me share your electron, and let me just hold on to it and keep it with me most of the time. So hydrogen just has 1. It would like 2 to be like helium, right? Hydrogen's the simplest element in the whole universe, and it's the most common by far. Go anywhere in the universe, you'll find plenty of hydrogen. It would really like 1 more electron. So if oxygen says, hey, I'll share an electron with you if you share your electron with me, and then we'll both feel special and good about ourselves. And so hydrogen pairs up with it, but oxygen holds on to the electron from hydrogen much more tightly than hydrogen can hold on to the electron from oxygen. Oxygen's more electronegative. So oxygen pairs up with 2 different hydrogens and forms H2O, right? Water. So water is a very stable molecule because oxygen has what it wants, 2 electrons. Each hydrogen has what it wants, one more electron, but nobody's giving anybody anything, they're sharing. So hydrogen's one electron, one of oxygen's electrons, they form a pair like that. So the hydrogen feels like it's got two. Really, most of the time, those electrons are being over at the oxygen side of things. And just one note about carbon. Carbon is 1, 2, 3, 4 steps away from a noble gas. It can form 4 bonds. And because of this, you can do all sorts of things with it. You can take a carbon and stick it to another carbon, stick another carbon there and another carbon there, and each carbon will then have, they'll share with each other, right? And they'll share with the guy on the side. So that uses up 2 bonds, but that means there's a bond up and a bond down. So you can have long, long chains of carbon, and then you can stick all sorts of things to them. Everything that's plastic is made of carbons in chains, and just depending on what we put on the carbon branches, it's mostly hydrogen, it's mostly hydrocarbons, all oils, gases, those are for fuel, those are all hydrocarbons, and then we can add different little side groups and change the properties. Carbon is also very, very important to living things. Carbohydrates, carbon, carbo, oxygen, hydrate is hydrogen. So carbohydrates are just carbon, hydrogen, oxygen. Proteins, carbon, hydrogen, oxygen, plus nitrogen and often sulfur and phosphorus and a few other things. But carbon, nitrogen, oxygen, or carbon, hydrogen, oxygen, plus nitrogen. Lipids are just carbons and hydrogens, long chains of carbons with lots and lots of hydrogens. And that's mostly what a lipid is. Okay, enough about the periodic table. What does a football stadium have to do with anything? This is a more correct model of the atom, and you'll see why we don't draw atoms in true form very often. So imagine, if you will, a golf ball in the center of the football field, and you can't really see it from here, but there it is, one golf ball. That golf ball contains all the protons and neutrons. That is the nucleus. Okay, so if the nucleus were the size of a golf ball, the electrons in their clouds would be zipping around the stadium. They would be smaller than marbles. They would be like little BBs, maybe not even that big, like a tiny little BB traveling at light speed. Each electron will at light speed, 186,000 miles per second, or whatever it is. Yeah, I think that's right, 186,000 miles per second. So in 1 second, you can see why we just draw electron clouds, because we can't say where those electrons really are at any one point in time. And in fact, they leave, they go places and they come back. Oh man, I just had like an electron go to Greenland and it came back to me. Why did it go to Greenland? I don't know, but it can do that because it's traveling at light speed and then zims off. So an interesting thing though, if an atom is made of a golf ball in the center that has, say, 6 protons in it, and there are 6 electrons buzzing around someplace in this stadium, you can imagine one golf ball plus 6 BBs, and that's the whole atom. The stadium is empty. In other words, an atom is almost entirely empty space, which, if you take it to its logical extent, you are almost entirely empty space. The chair you're sitting on is almost entirely empty space. It's very weird to think about, but this is why we don't really draw atoms correctly, because we can't, because they're mostly empty space. 99.99999999996% empty. Wow, that's a lot of empty space. So why don't they just pass through each other, objects? You're levitating, actually. It's kind of weird, but when I do this, it's I'm not actually touching my hands together. The electron clouds, when they get close to each other, they repel each other. It's really weird to think about, but it's this electromagnetic repulsion. And so the atoms just can't get any closer together because they repel each other. But it's weird. You're mostly empty space, almost entirely empty space. And in a plasma situation, in a star, the electrons get ripped off from the protons, and the things are much, much, much more dense. And so Thor's hammer is supposedly made from like a collapsing star, the densest stuff in the universe. So if you had a hammer, that much matter, if you took those atoms and took away the empty space, Thor's hammer would have a gravitational pull to it that would knock the moon out of orbit, because you might be able to fit the whole moon into the hammer, basically. Certainly you could fit all of a university campus in a teaspoon if you if you got rid of the empty space. So in a star, the empty space is gotten rid of, and so it's extremely dense. And it's that huge density that creates giant pressures and temperatures that creates the fusion reactions. And a star gives birth to all the other elements. So I said you're made of carbon, hydrogen, oxygen, things like that. All that was born in stars. You are made of star stuff, which is pretty cool. The universe is mostly hydrogen, second helium, but you're made of carbon. Yeah, you're made of hydrogen too, but nitrogen, oxygen, phosphorus, sulfur, sodium, magnesium, calcium, potassium. These are heavier and heavier elements. As you go down further in the table, they're heavier and heavier elements. Those are all made in stars. Our whole planet, is born of stars. It's pretty cool to think about. Okay, on to molecules. You can stick atoms together. So we were talking about atoms and pure elements, but atoms, they can stick together. And here's propane. And it's got 3 carbons. They're bigger. That's in gray. And 8 hydrogens. How do you get 8 hydrogens? Well, here this carbon attaches to this carbon, which is also attached to that carbon. So this one has 2 spaces that it can, grab onto 2 hydrogens. This one isn't attached to another carbon over here, so it has 3 spaces. Each carbon can form 4 bonds. So it grabbed onto 3 hydrogens, and so did the one at the other end. That's propane gas, and it's a pretty small molecule with just 3 carbons and 8 hydrogens. Here's a fun thing: sulfur hexafluoride. This is a heavy gas. I want to show it to you. If I can get my link to work here. How am I going to do this? Let me just do sulfur hexafluoride, and we'll do a video. There's some really funny videos with sulfur hexafluoride, but it's a very it weighs a lot more than nitrogen, which is our air is mostly nitrogen and oxygen. And anyway, this weighs quite a bit more, and I need to figure out how to, just a second. Not missing too much here yet. Okay.
But here, watch this. I'm going to slowly pull the lid off. Okay. So that should be perfect. Gary, would you take that little end off over there as well? You see that? Yeah. Yes. All right. So let's see if it feels pretty good. So let's see if we can float the boat. Okay. Ready? So here we go. Let's see if we can float the boat. Stay there, little guy.
Hopefully you're seeing this.
Amazing. That is awesome. So is that? It's okay. Push it around. It's okay.
So it's floating on this heavier gas, which is contained in this container. So that's really cool. But here he's showing a taser. and how it doesn't work inside the sulfur hexafluoride. It's completely non-conductive gas. And then here, they're breathing it in. All right, hopefully you got that. Sulfur hexafluoride, pretty awesome. So it is a heavy gas, and you can search for Steve Spangler science or sulfur hexafluoride. You can find that. There's some funny pranks and different things with it. So anyhow, sulfur is just a bigger atom than nitrogen or oxygen. Fluorine is a pretty big atom. So there's a fairly, heavy molecule, but it's still pretty small compared to something like this. This is massive. Each dot is an atom. So this is a giant molecule with thousands of atoms. This is a protein. Your cells make this kind of thing all the time. And why do they make proteins? It's not, you think protein, you think muscle. Most of the time, most of your cell's proteins are enzymes, and enzymes are tools for doing things inside the cell. So you make tens of thousands of enzymes. And honestly, we don't know what most of them do. But they each do a job in the cell. And this is a cool thing that we're just really kind of learning more and more about, is what, how these different enzymes work. What do they all do? So most of your genes give instructions to make enzymes, which are proteins that look like this, some huge protein, and the shape really matters. These are tools, and if your wrench wasn't the right shape, it wouldn't work. These enzymes are not the right shape, they don't work. But I just wanted to show that this is a really massive molecule. DNA is a really massive molecule. And your nylon stockings, those are really massive molecules too. Built by, it's a polymer, long strings of repeating subunits. So I'll just quickly show you that. We'll end on that. This is the end for chapter 13 finally. So if you search for making nylon, nylon, the first result's a good one here. Let's skip ahead. He's mixing
layers floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm going to reach in here, and where the interface is, I'm going to pull out some nylon. So here we go.
Look at that.
We'll see how much nylon we can pull out of this thing. There's a meter.
So he's making big long molecule. That's one continuous molecule.
Set for this. And
okay, so as he pulls that out, it's just the reaction, the atoms are forming molecules and sticking to each other, and it's just a longer and longer and longer and longer chain of molecules. It's called a polymer, where you have many subunits stuck together. So that's organic chemistry. It's pretty cool stuff. We're going to end there for now, and then I will try to make a separate video talking about chapter 14, 15 a bit, but for now, I'm afraid I have to stop here. So bye for now, and good studying.